grade 12s. For this lesson, what we're going to do is we're just going to take up the bottom question on page number 16. Just make sure we've got all of our vocabulary for what this electrochemical cell is going to look like if we were to do this in the lab. Then we're going to look at cell potential, and there's a bit of math that's involved in this lesson. Okay, so here we go. So once you've got your electrochemical cell, and in this question, it says that you're going to use zinc and copper, and it's showing you the cell notation. So do you remember that this is what's called the cell notation? So it's telling me that on the left-hand side of the salt bridge is the anode. This is where oxidation occurs. The zinc atoms are going to turn into zinc ions. And on the right-hand side of the salt bridge, it's telling me that it's the copper ions that get reduced into the copper atoms. So that's called the cell notation. And based on that, it tells me which way the direction of the electrons is going to flow. Okay? We know that this reaction would look like this if we were to put it together with all of the states. And we also know that when you've got this cell set up, the metal strips are going to be in a solution that's a nitrate solution where those ions are also available. Okay, so let's add a few of the labels to the diagram. Okay, first of all, up at the top, there is our voltmeter. That's going to control and read the number of electrons as it runs through the wire. Remember, you could put any other load on here, like you could put a fan, you could put a light bulb, you could put a motor there, anything that's going to be able to capture those electrons. Essentially, we're making electricity, right? Which way do the electrons go? Well, we know that the anode is where oxidation occurs, okay? So anode, site of oxidation. So I'm just adding a lot, I'm running out of space there. I'm just adding a lot of labels to this little diagram right here. And I'm going to try to do that without having a ruler. So obviously when you're doing a nice science diagram, you want to make sure you've got a ruler, all straight lines out to the side. Do you remember doing that okay? I do not have a ruler, so I'm just going to wing that there. Okay, so there's my anode. That's my site of oxidation. The electrons are going to flow this way through the wire all the way to my cathode, which is the site of reduction. Okay, copper is my cathode and my anode is my zinc. How many electrons are flowing through? Well, if it's a zinc and it's going to a Zn2+ ion, then clearly 2 electrons are flowing as they move. For every zinc atom, it turns into a Zn2+, therefore I've got a flow of electrons of 2 going and being read through that voltmeter. Okay, this is a wire lead, and I'm going to just label in where my solutions are. So the copper is in a solution of copper nitrate, and my zinc is in a solution of zinc nitrate. Now, I know that's a little bit hard to see, but remember, this is a little tiny ceramic porous cup, and picture that little tiny cup sitting into a bigger beaker, and so the whole little cup is sitting into a beaker that's filled with the zinc nitrate. Okay, I'm going to show you what that looks like when we do the tutorial in the afternoon. So come to the tutorial and I'll show you what that setup looks like. It's hard to do. I did not bring that home with me. Okay, all right, what else do we need to add on here? We need to show what happens to the electrons. Okay, so this is making a complete diagram. I want to show that at the anode, the zinc atoms turn into Zn2+ ions. I want to show that the copper ions, which are in the solution, the Cu2+ ions, okay, these ones get reduced. They go directly onto the copper. And then what I want to show is I want to show the flow of the nitrates, okay, because they're not reacting at all, but the nitrates do have a negative charge. They're going to flow across that porous barrier to balance out the charge that builds up that's the opposite. Okay, so which way shows the net movement of the nitrate ions across the porous cup? Clearly they're going to go this way. Okay, the net ionic movement of the nitrates is going to go from the copper nitrate over to the zinc. Why? Because you've got a huge zinc positive charge building up and you want to be able to keep the electrons flowing through. So this acts just like the salt bridge does if you have an electrochemical cell set up like this, where they are physically separate in two different beakers, then your nitrate or your ammonium are going to go one way or the other based on the charge as well. And I already explained that in the last one. Okay, I know the last thing we can add, we can look at our diagram here and show which of the metal strips, the anode or the cathode, are they going to increase in mass or decrease in mass, okay? So remember that this one over here, the zinc is going to start to get smaller and smaller. At the same time, the copper is going to get fuzzier and fuzzier. It's going to build up with copper, and that lead will increase in mass. And we'll do a little bit of calculations on our very last day where we can add in some stoichiometry to show how much mass based on the number of moles that are either oxidized or reduced. Okay, that looks pretty good there. Any questions about that one? Just let me know, okay? All right, we're going to move on to looking at the cell potential. And this is where, if you're given the values, as opposed to just exploring in the lab to see which way the electrons go, you can actually look them up on a table, and based on the reduction potential, it'll tell you which one is going to get reduced and thereby which one's going to get oxidized, okay? So what do you need to do for this one is you need to find this table in your textbook. This is the table that I would obviously give you on our unit test. So you want to make sure you can read the table and be able to use it. There's lots of questions at the bottom of this page to try, okay? So this essentially is, what is the potential of this cell, electrochemical cell, this battery, if you will. What's the number going to read on the voltmeter? Okay, here's how you figure this out. So E value of the cell, just see how I've written this? E value of the cell is the cell potential. It's just a short form way of showing that, okay? Here's another way of showing that. E with a little zero at the top, that's called a naught. E to the naught, that also means cell potential, okay? It is the electron attracting ability of a half cell. So the difference in this electron attracting ability between the two half cells is called the potential of the entire cell itself. Okay, it's not as tricky as maybe it sounds, so let's work our way through this. So what is the potential of the half cell? So we're looking at reduction potentials. This is the table that you're going to be looking at in the textbook, okay? And then I want you to find hydrogen on that list. An arbitrary value of 0 volts has been assigned to hydrogen, the hydrogen ion half reaction at standard conditions. And when we say standard conditions, we mean 1 mole per liter, 25 degrees Celsius, and 101.3 kilopascals. That's standard temperature, pressure, and ionic concentration. They've labeled the reduction of hydrogen, okay, as 0, arbitrarily assigned. Everything else is going to be compared to that value right there. So you can see that it's written as a reduction. Gaining of electrons reduced, the gaining of electrons that's on that side, that is written as the reduction, okay? So the above half cell is the reference standard for determining the other half cell potentials. By determining the voltage of hundreds of half cells coupled together, then you can experimentally measure the difference in potential between them, okay? So then what you get is, by convention, the standard half cell reaction is always going to be written as a reduction. It's always going to be shown in this table comparing reductions. Once you've figured out which one is going to actually get reduced, the other one will by default be the oxidation. You'll take the reduction potential and write the one that gets reduced as a reduction, the one you're comparing it to as an oxidation, and add the two values together to give you the potential of that cell. So if you had those two metals and those two ions available in the solution, which way do the electrons flow? And can you make the electrons flow so that you get a positive read on your voltmeter? Okay, so here we go. Once again, you're going to read it. The E0 value for a half reaction is negative. The half reaction has less of a tendency to gain electrons than hydrogen does if hydrogen is 0. And if the E0 value for a half reaction is positive, then the half reaction has more of a tendency to gain electrons than hydrogen. Okay? So now let's see what would be the voltage if you compared magnesium and potassium. So picture magnesium metal, potassium metal in a solution of magnesium and magnesium nitrate, potassium and potassium nitrate. Which one gets oxidized and which one gets reduced? Can we use the values in the textbook to help us figure that out? Yes, we can. Could we do this in the lab? Yes, we can. We could set up the leads attached to the voltmeter. Whichever one gives me the positive reading would show, right? The electrons flow this way, then this is the anode and this is the cathode. If the electrons flow this way, this is the anode and this is the cathode. Okay, whichever one combination gives me a positive reading on the voltmeter, then I know that you're going from the anode to the cathode because the anode is the one that gives off the electrons, right? It's the one that gets oxidized. Okay, so let's go back. If you were given this question of magnesium and potassium, I want you to look up the two values in the standard reduction table. Okay, so go to the textbook, find these two. You'll see that you read, because it is the reduction value, it shows you the potassium in the reduction way, and it shows you the magnesium in the reduction way. Every value on that reduction potential table is a reduction because it's a reduction potential table. Your job is to look at the E0 values, okay, and figure out which one of these two, if they were together, would actually get reduced and which one would get oxidized. Okay? The half reaction with the smallest E0 value or the greatest positive number. So think of the scale tilted up and down, your integer scale, 0 here, positive values, negative values. Okay? The one that's closest to the positive has the greatest potential to be reduced, and it will get reduced when it's in combination with another one below it. Okay, so I've written this on the side, add this to your note. The oxidizing agent has the highest positive reduction potential. It is the best oxidizing agent, and therefore it is the one that gets reduced. Okay, so again, step number 1, I open up the table in the textbook. Step number 2, I find my ions that I want to compare. This question says compare magnesium and potassium. Jot them down. Then I look at these two and I compare these values. Which one's the most positive value? This one. That means that magnesium has the greatest potential to be reduced, so it does get reduced, and the potassium will get oxidized. Okay? The magnesium has the greatest potential to be reduced because it's the highest positive value of the two. Therefore, it will get reduced, and then the potassium is the one that's going to get oxidized. Okay, I write them down as such down below. So here I go. I know that it's going to be the potassium that gets oxidized. So you can see I've got the reduction potential. I need to write that as oxidation. So I need to flip it. I need to show that this is actually going to be how it's going to take place. Notice what happens to the E0 value. Okay? I need to flip it to show oxidation. You need to take that negative 2.92 and show it as the oxidation. So you need to reverse the sign. Okay? Now that I've got my reduction and my oxidation, I know which half reaction is going to go which. Then I'm just balancing with my electrons like normal. Okay? And I'm just going to add in, the only thing that we're adding in is the E0 value, because I want to see what will the value of this cell look like if it reads through the voltmeter. So my oxidation is written as such. Notice that I have to multiply it by 2, but of course you're going to get there because you're going to have a reduction of your magnesium. Recognize the fact you've got 2 electrons per magnesium. So to have a balanced equation, I need to balance out the 2 electrons gained by magnesium. You have to reflect that potassium to have lost 2 electrons. So I multiply that half reaction by 2, 2, 2. We've been doing this for a couple of days now. It does not affect anything over here with the E0 value. The only thing it affects was the fact I flipped the sign to show oxidation. I do my net reaction, cancel out my electrons. I have a simplified net reaction. And what do I do to the E0 values? I add them up. So if I had magnesium and magnesium nitrate, potassium and potassium nitrate, I connected them to a voltmeter, what would the number on the voltmeter read? It would read positive 0.58. Okay, this potassium is going to be the anode because that's the site where the oxidation will take place. This would be the cathode. You could do a little drawing to show what that would look like in the lab, but here's where you figure out using the reduction potential table which one's going to get reduced, and then you simply flip the other one to show oxidation. Add the 2 values for those half cells together, and you end up with the E0 value for the cell. Okay, now there's lots of notes here. Note, if the half reaction is reversed, the E0 value is reversed, all you're doing is flipping the sign. Note, by multiplying that half reaction by 2, it does nothing to the E0 value. And I want you to just remember that because when we get to our unit number 3, we're going to be doing a little value there with some energy in a reaction. And if you're multiplying values, you will add a multiplier in. So note for electrons, it's just reading the electrons through the voltmeter. It does not have any multiplying effect on it. Okay? All right, so here you go. You're going to be doing the assignment questions number 1 and 2. And I want you to pay careful attention to question number 2 because this is like the hard part where you're looking at some of the values and it's like, well, which pair is going to give you the largest voltage and which pair combination is going to give you the smallest voltage of these ones up here. So just make sure you're looking them up in your table and that you can do that. Okay, one little disclaimer. There is another way to calculate the cell potential that you might come across. And it's a formula where you take the E0 value of the cell, you do the cathode, subtract the anode, and then you're not flipping the value of the negatives. Don't get confused with the other way to calculate that. It may be in the solution set, but it's definitely one you're going to come across. But you don't want to change a negative to a positive and then change it back again. You either write them as oxidation reduction and add them up, or you do a formula where you're subtracting. Don't worry about that second part. Okay, so good luck with those questions. Let me know how it goes.